Hello everybody, my name is Sashwat Sristamali. I am a postdoc researcher in the Kondo Laboratory at Keio University. Thank you for attending this presentation. I will be presenting our paper FAWS, Fault-Aware Weight Scheduler for DNN Computations in Heterogeneous and Faulty Hardware. Deep neural network accelerators like GPUs and TPUs have become very popular recently, and these accelerators contain a lot of densely packed cores to maximize parallelization. However, at such levels of integration, there is a possibility that some of these cores are faulty. This is partly due to manufacturing defects or degradation with age or due to marginal operation. It is also possible to operate these accelerators at reduced precision for lower latency and high throughput. As a result, the computations are corrupted, leading to errors. Fortunately, neural networks are quite resilient to errors and degrade gracefully with increasing error probabilities, as shown in this 2016 paper by Regan et al. This is partly due to the overprovisioned parameters in neural networks and independent computations within a layer. In fact, due to their resilience, it may be possible to purposefully increase error rates to extract higher energy efficiency and lower latency. There has been some considerable research into leveraging the neural network error resilience for performance and energy gains. In the Minerva and Ares papers, the authors use voltage scaling in which they reduce the operating voltage for SRAMs for energy gains. To compensate for the increased bit errors, they use a mechanism to detect and correct these. Another proposed alternative has been to perform a neuron sensitivity analysis on the neural network and then allocate the least critical neurons to inexact, cheap, or approximate hardware. Using reduced precision has also been one of the most popular techniques to achieve this. Many specialized hardware optimized for specific models have already been proposed. Most previous approaches rely on neuron sensitivity, but we have to keep in mind that a neuron is actually a computational concept. In reality, the computations corresponding to a neuron are spread out among many cores during parallelization. For example, if we look at a CUDA's block tiling method, the computations associated with a neuron are spread out among multiple PEs, and each PE may participate in the computation of multiple neurons. In short, there is no one-to-one mapping between neurons and hardware PE. In this work, we shift the paradigm from scheduling unimportant neurons to scheduling unimportant computations on compromised hardware without interfering with the optimizations that reduce cache misses, shared memory, and/or banking conflicts. So, to recap, neural networks will be deployed in various possibly faulty hardware platforms. The hardware may be faulty due to degradations due to age degradations or defects, or due to marginal operation for performance gains. Each hardware will have different fault profiles and degrade the model performance in a different way. Some of this degradation can be recovered by scheduling unimportant computations to compromised hardware. But since there are so many variations of the hardware and neural network model types, we require a general scheduling method. An alternative is to retrain the models, but this is not always possible due to lack of access to training data or sometimes even computational resources. So we introduce FAWS, Fault-Aware Weight Scheduler, that reschedules computations so as to recover the neural network performance from degradation caused by compromised hardware. The basic idea is to reshuffle the rows of the matrix during matrix multiplication such that important computations get allocated to non-faulty hardware. By doing so, we can recover significant model performance in faulty hardware as compared to naive scheduling method. We focus only on inference for now. The challenge is now to find the best shuffling order. For a matrix with n rows, there are n factorial permutations, so the search space is extremely large. So we employ genetic algorithm to search for the best shuffling order. In our work, we model the hardware faults using a bit-level error injection method. This is similar to the method proposed by Regan et al. In their 2016 paper. For the sake of example, we assume an NVIDIA GPU in our work and further assume the faults take place in the SRAM cells of the CUDA core registers. We evaluate three different types of faults. First is flip to 1 or flip to 0, where a random exponent bit of the floating point data is stuck at either 0 or 1. This is to model faults due to permanent damage such as shorts and opens. The other fault model is the bit flip model, in which a random exponent bit is flipped from either 0 to 1 or 1 to 0. This represents intermittent faults due to timing delays, crosstalk, or marginal operation. And finally, we look at reduced precision, which is technically not a fault, but we model them as one because it makes for easier analysis and description. We'll look at TF32 and BF16 data types in which chunks of the least significant bits of the mantissa are zeroed out. To simulate the faults, we assume each CUDA core has a fixed fault probability or fault rate, and the fault profile of the GPU determines the fault rate of each of its CUDA cores. In this picture, we are looking at a GPU with 20 streaming multiprocessors, and each streaming multiprocessor has 32 CUDA cores. The color indicates their fault rate. At each instant of time, a CUDA core is either faulty or not faulty, and this is determined through binomial sampling, and the probability is determined by its fault rate. So let's see how FAWS actually works with a toy example. We have a matrix with 3 rows and an accelerator that has 6 different cores. And what we need to do is we need to multiply this weight matrix with this feature vector. The cores are arranged into groups of 3 into 2 streaming multiprocessors with varying fault profiles. C0 and C3 are the least faulty ones, whereas C1 and C5 are quite faulty. The weight matrix is divided into 6 tiles and assigned to each core to multiply with the corresponding value in the feature input vector. Let us assume that the weights in the green row are the most critical, and we would like them to be allocated to the least faulty cores. After GA optimization, we get the chromosome. The chromosome is fed into the fault-aware weight scheduler, and the rows are shuffled such that the green row is now on the top and assigned to core C0 and C3. Now the matrix vector multiplication takes place, and after the multiplication, we get the partial products from each of the streaming multiprocessors. Now we look at how we simulate the actual faults by injecting faults after the computation. Hardware faults are simulated by binomial sampling using the fault rates given here. After binomial sampling, we see that core C1 and C5 are faulty, as indicated by the grayed out boxes. So as a result, their corresponding computation results are corrupted. The final result is the sum of these partial products, and then FAWS finally reshuffles these results back to the original order so as to get the correct answer. If the row shuffling was not done, the dot products of the critical weights, basically the green row with the feature vector, would be corrupted, and which would result in high performance degradation. However, by shuffling the rows, we can see that this the green dot product is free from any computational errors. This slide shows how the chromosomes represent the shuffling order. Before the GA optimization, they are in their natural order 0, 1, 2 and are assigned to these cores. But after GA optimization, this is the better shuffling order as determined by the process. Now we move on to the evaluation methodology and results. We evaluate FAWS on 2 Linnet type CNN models, MNIST32 CNN that uses the MNIST handwriting dataset, and the Fashion CNN model which uses the Fashion MNIST dataset. We assume we are already given a trained neural network model that needs to be implemented on a faulty hardware accelerator. We assume the hardware accelerator is an NVIDIA GPU with 20 streaming multiprocessors, with each streaming multiprocessor containing 32 CUDA cores. We generate the different random hardware profiles characterized by different fault rates. We then evaluate each model with each fault profile with different random seed initializations for statistically significant results. In the interest of time, we will only discuss the results for MNIST32 here. This figure shows how flip to 1 and bit flip errors degrade the model accuracy. First, we observe that as we increase the fault rates, the accuracy drops gracefully. Secondly, we see that the convolutional layer C0 is most sensitive to the faults in the hardware. This is because the kernel elements of the C0 layer are reused many times. So if important kernel elements have corrupt computations, it affects the performance very much. We will now see if FAWS is able to recover any of the drop in performance by shuffling the rows. For analytic purposes, we implement row shuffling only on the C0 layer, since the degradation due to the other layers are not very significant. We observe that the original accuracy in a non-faulty hardware is about 98%. When the errors are introduced, and the bit error rate is about 0.005, the accuracy drops to about 58%. By using FAWS and shuffling the rows, the accuracy rises back to almost 85-90%. We get this performance recovery by simply shuffling rows, which has almost no computational overhead and corresponds to large power savings. What this means is that it is possible to operate SRAMs at aggressively low voltages to save energy. If you look at this chart here, we can drop the supply voltage all the way down to below 0.7, which gives us more than almost 50% power savings. Of course, this increases the bit error rate to 0.005, but as we can see with FAWS, we can shuffle the rows such that the corresponding performance degradation of the model is not so significant and that it is tolerable. Next, we'll look at how MNIST CNN model is affected by flip to zero and reduced precision errors. From the figure, we can observe that flip to zero is mostly benign and doesn't degrade the model performance even at high fault rates. This is primarily because a neuron is generally more likely not to fire than to fire, so flipping a bit so as to suppress the neuron firing doesn't have a drastic effect. Now we focus our attention to the effect of reduced precision, that is truncating the least significant bits of the mantissa. We observe that aggressively reducing the precision affects the penultimate hidden layer H2 and the output layer OP the most. This may be primarily because the output layer is the most sensitive to precision between the values due to the presence of a softmax layer. We use FAWS on both H2 and OP layers to see if we can recover any of the performance degradation due to reduced precision. By simply reshuffling the rows of the matrix, we can recover as much as 5 percentage points when using reduced precision. As expected, we have greater recovery in the output layer. Keep in mind that we have simulated a scenario in which the PE cores can randomly change their precision, which is really not realistic. A more realistic scenario would have more deterministic and controlled mixed precision schemes. In such cases, we can expect FAWS to get higher model performance recovery. So, in conclusion, we know that due to dense technology integrations, accelerators can be quite faulty. However, the neural networks are quite resilient to these faults, and we can recover some of their performance by scheduling unimportant computations to compromised hardware by shuffling rows. We propose FAWS to achieve this, and we find the best shuffling order using GA. FAWS can recover almost 30% of performance, which corresponds to very large power savings, and this is all in a very cheap, this has no computational overhead, and it's a black box optimization process, which is independent of the type of model or the hardware. So this is the end of my presentation. Thank you for listening. I would like to thank my co-authors Yuan Hei and Masaki Kondo. Also thanks to GST Mirai for funding this project. Thank you very much. Your questions, comments, and feedback are most welcome.